The paradox of the Hilbert Hotel. First up is the Hilbert Hotel paradox. This thought experiment was conceived by the German mathematician David Hilbert, and it challenges our everyday notions of infinity. Imagine a hotel with an infinite number of rooms, all occupied. You might think there's no room for more guests, but here's the twist. An infinite hotel can always accommodate more, even when it's full. By simply shifting each guest to the next room, the first room is freed up, ready for a new occupant. This paradox demonstrates how infinity behaves in ways that defy our finite understanding. The Galilean paradox. Next, we have the Galilean paradox. This paradox arises when we compare the set of natural numbers with the set of their squares. Intuitively, one might think that the set of squares should be smaller than the set of natural numbers since not every number is a perfect square. However, by pairing each natural number with its square, we find that both sets have the same size, or cardinality, in terms of infinity. This paradox highlights the counterintuitive nature of infinite sets and the concept of one-to-one correspondence. Zeno's paradoxes. Zeno of Elea introduced several paradoxes that question the concept of motion and division of time and space. One of his most famous paradoxes is the dichotomy paradox, which argues that to reach a destination, one must first cover half the distance, then half of the remaining distance, and so on. This infinite division suggests that motion is impossible because it requires completing an infinite number of tasks in a finite time. Zeno's paradoxes challenge the very foundations of mathematics and physics, forcing us to rethink how we understand motion and time. Russell's paradox. Bertrand Russell presented a paradox that shook the foundations of set theory. Russell's paradox arises when we consider the set of all sets that do not contain themselves. If such a set exists, does it contain itself or not? If it does, then it shouldn't. If it doesn't, then it should. This self-referential paradox reveals the inconsistencies in naive set theory and led to the development of more rigorous mathematical frameworks. It underscores the challenges of working with the concept of infinity within logical systems. The Banach-Tarski paradox. The Banach-Tarski paradox is perhaps one of the most mind-bending. It states that it's possible to take a solid ball, divide it into a finite number of pieces, and then reassemble those pieces into two identical copies of the original ball. This paradox relies on the axiom of choice, a controversial principle in set theory. While it's impossible to perform in the real world, the Banach-Tarski paradox challenges our understanding of volume, space, and the infinite divisibility of matter. The Grand Hotel paradox. Similar to the Hilbert Hotel, the Grand Hotel paradox explores the bizarre properties of infinite sets. Imagine an infinitely large hotel that can accommodate not just an infinite number of guests but an infinite number of buses, each carrying an infinite number of passengers. This paradox extends the Hilbert Hotel concept, showing that infinity can be manipulated in seemingly impossible ways, reinforcing the idea that infinity is not just a large number, but a concept that defies conventional logic. The paradox of the infinite lottery. The infinite lottery paradox delves into the concept of probability within an infinite set. If there's an infinite number of lottery tickets, each with an equal chance of winning, or the odds of any particular ticket winning, the paradox arises when we try to calculate probabilities within infinite sets, revealing that standard notions of probability break down when applied to infinity. This paradox highlights the difficulties in applying finite concepts, like probability, to infinite scenarios. The Burali-Forti paradox. The Burali-Forti paradox, named after the Italian mathematician Cesare Burali-Forti, emerges from the concept of ordinal numbers, which are used to generalize the notion of sequence order. The paradox arises when we try to construct the set of all ordinals. Since each ordinal number is defined as the set of all preceding ordinals, the set of all ordinals should itself be an ordinal. However, this leads to a contradiction because it implies the existence of an ordinal that is both smaller than and larger than itself. The Burali-Forti paradox reveals the complexities and potential inconsistencies when dealing with infinite sets within set theory. The Superman paradox. The Superman paradox, also known as the infinity machine paradox, explores the concept of an infinite sequence of actions completed in a finite amount of time. Imagine a machine or an entity like Superman who can complete a task in half the time it took to complete the previous task. As these tasks have in duration infinitely, they appear to allow an infinite sequence of actions to be completed in finite time. This paradox challenges our understanding of time, continuity, and the limits of physical and mathematical operations. The paradox of Tristram Shandy. The Tristram Shandy paradox, named after the protagonist of Laurence Sterne's novel, explores the relationship between infinite time and infinite tasks. In the story, Tristram Shandy is writing his autobiography so slowly that it takes him 1 year to document a single day of his life. If he lived forever, could he eventually catch up to the present day? The paradox suggests that, given infinite time, even the slowest process could theoretically be completed, which challenges our intuitive understanding of progress and infinity. The arrow paradox. Zeno's arrow paradox is another famous thought experiment that questions the nature of motion. It posits that if we observe an arrow in flight at a single instant of time, it appears to be motionless, since in that instant, it occupies a fixed position. If at every instant the arrow is stationary, how can it be moving at all? This paradox forces us to reconsider the concept of motion as a series of instantaneous still frames and challenges the very notion of continuous movement in space and time. The paradox of the infinite regress. The infinite regress paradox arises in various philosophical and logical contexts. It occurs when a proposition or process requires the completion of an infinite sequence of steps before it can be resolved. For example, the classic question of what caused the first cause leads to an infinite regress, where each cause requires a prior cause, and so on ad infinitum. This paradox challenges the concept of causality and raises questions about the nature of existence, time, and the universe itself. The surprise paradox. The surprise paradox, also known as the unexpected hanging paradox, involves a situation where a prisoner is told they will be hanged on one day of the week, but the day of the hanging will be a surprise. The paradox arises when the prisoner logically deduces that a surprise hanging is impossible, yet the surprise still occurs. When expanded to an infinite timeline, this paradox challenges our understanding of logic, expectation, and prediction within infinite or indefinite contexts. The Olionos paradox. The Olionos paradox is a lesser-known thought experiment that explores the nature of infinite sets within physical space. Imagine an infinitely large universe with an infinite number of stars. If every star emits light, how can the night sky be dark? This paradox, also known as Olber's paradox, raises questions about the nature of the universe, the distribution of matter, and the implications of an infinite cosmos on our observation of space. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video if you found this video helpful, and subscribe to the channel for more such amazing videos.